Now, in this lecture, we calculate the density of states for a superconductor. Now, if you recall, we had calculated this energy Ek spectrum, or the energy dispersion Ek, which is square root of Ek square plus delta square, and for a free electron, this is the dispersion at the Fermi energy, and for a electron from and for an electron in a pair, okay, the energy will go like this, okay, where the minimum energy of the electron is delta. Okay, so these are single electron states. Okay, this is the single electron, okay, when delta is not equal to 0. Okay, and this is for a single electron in a normal metal, say, where delta is anyway 0. There is no gap in the density, there is no gap in the superconductor. Okay, so delta is equal to 0. So you can see that no electron can have an energy which is less than delta. Okay, so at k equal to kf, we know ef ek measured with respect to the Fermi energy is plus minus delta. Okay, so now if you want to calculate the number of states, okay, which are around the Fermi energy, okay, then qualitatively, if you want to, so this is your Fermi energy. If you want to calculate the states which are around the Fermi energy, okay, for the spectrum, okay, or the number of Ek states which are available around the Fermi energy beyond delta, then you can see that if you calculate, this is state 1, okay, and if you go infinitesimally close, you will have a lot of states which are very closely spaced. Okay, there is a very high density of states near the gap delta. There is a very high density of states near delta, but then as you start moving away from delta, the states, then the density becomes less. So very near delta, very near the Fermi energy, there is a very high density of states which are around EF plus delta or EF minus delta. So around the gap, okay, around the boundary of the gap, there is a very high density of states that comes because of the nature of this dispersion of electrons in the superconducting state. Okay, and as you go away from delta, then the density becomes less, as you can see here. Okay, so let us try and calculate this nature of the spectrum. So we want to calculate the density of states. Now if G represents the density of states, remember that okay, so what we are saying is that in the superconductor, the energy E is equal to Ek, which is square root of Ek square plus delta square, and in a normal metal, the energy Ek is nothing else but square root of Ek square, because delta is 0. So therefore Ek is equal to small ek. Okay, so the total number of states, whether in a superconductor or in a normal metal, is the same. Okay, this has to be. Okay, the total number of states which are available is not going to change when it becomes a superconductor or it becomes a normal metal. The total number of states is going to remain constant. Okay, so it's just the densities, the distribution of these states will change depending on once it becomes a superconductor or once it becomes a normal metal, because it depends on the nature of the dispersion. What is the nature of the dispersion, that is going to change the distribution. But the total number of states, which is, this is the total number of states in the superconductor, and this is the total number of states in the normal metal or material. They are going to be exactly identical. Okay, so now in the normal metal, G of Ek is going to be represented by EF, because we are basically going to look at the density of states distributed around the Fermi energy. Okay, so we will we will consider the density of states which are around the Fermi energy. So we will look at the density of states around the Fermi energy. We want to calculate the density of states around the Fermi energy, that is EF plus minus delta. Okay, so if I go to this is delta is typically very small. Okay, the Fermi energy is of the order of few electron volts, and delta can be few milli electron volts. Okay, just to give you an example, that delta is equal to 2 h cross omega d exponential of minus 1 by v naught into GeF. Now if h cross omega d is of the order of 100 Kelvin, okay, which is typically in the case of many materials, that the Debye frequency, the energy range associated with the Debye frequency is of the order of 100 kV, and V naught into GeF is, let's say, of the order of V naught GeF is of the order of 5, or 1 by V naught GeF is of the order of, let's say, 0.2, then delta, if you calculate using the above, will be of the order of about 4 Kelvin. Okay, so then this is much smaller than the typical Fermi energies which are present inside the system. So delta is definitely very small, and so if you are looking at around the Fermi energy, the density of states of the normal electrons will be approximately taken to be equal to EF. Okay, now so G of Ek in the superconducting state, okay, Gs of Ek dEk is equal to G of Ef, okay, into dEk. Okay, so the superconducting state Ek is equal to GeF dEk by dEk. Now Ek is square root of Ek square plus delta square, so therefore dEk by dEk is 1 by square root of Ek square plus delta square Ek. Okay, now therefore Gs Ek is equal to GeF into square root of Ek square plus delta square divided by Ek. You just have to put it here and you will get this. But inside a superconductor, the energies are in terms of ek, rather than measuring energies in terms of small ek, which is the energy of a free electron measured with respect to the Fermi energy. You measure the energies in terms of ek, so we can convert this into ek and write it in terms of ek. So square root of ek square plus delta square is capital ek, and small ek is nothing else but square root of ek square minus delta square. So therefore GS ek is this is the expression for the density of states around the Fermi energy. And now if I plot this density of states around the Fermi energy, you can see that if I plot GEK, so if this is the Fermi energy and I am just exaggerating it, EF plus delta and EF minus delta, then you can see that on approaching delta, when EK approaches delta, there is going to be a divergence. Okay, so you can actually take a in units of if I plot this as a function of ek, then this will be measured with respect to 0. Okay, so this is 0 plus minus delta, and then you can see that there is going to be a divergence around the density of states will show a divergence around the Fermi energy. The other way of looking at it, okay, if I plot it in okay, in either ways, this is going to be the behavior of the density of states, and this is what I had shown you earlier, that if I look at ek plot, okay, if I look at ek plot as a function of k, then this is of course for a normal electron. For a normal electron, this is the dispersion at kf, and the dispersion for the superconducting state is going to be like this. Then around, if I look at the density of states which are going, and this minimum is delta. So if I look at the density of states which are around delta, then these states are very closely spaced. If I look at around delta, these states are high density, and if I move away from delta, far away from delta, then I see that the states are reasonably well spaced out. Okay, so this is low density. This is low density of states. The total number of states whether superconductor or normal is identical, but because of the nature of the dispersion, ek spectrum dispersion, you can see that around delta there is a high density of states. This is the high density of states, whereas far away from it the density of states becomes low. The density is low. Okay, and this is basically your expression for the density of states inside a superconductor. You can see that around the gap within plus minus delta there is no states which are available. So within superconducting gap, no single electron states are available. So one other quick calculation that one can do is estimate the coherence length of the superconducting Cooper pair. Okay, to estimate that, let us recall that h cross square by 2m star kf plus delta k the whole square minus h cross square by 2m star kf minus delta k the whole square is going to be equal to 2 delta. Okay, this is in the momentum space. Okay, instead of writing in terms of the energy, if I look at in the momentum space, then within a delta k interval of kf, okay, I am going to have pairs which are present. Okay, and this is going to be so this is going to be the total energy of the system, which is going to give you your total binding energy. Okay, so this is around kf. So around kf, within plus minus kf minus delta k and within kf plus delta k, I am going to have pairs which are present. Okay, so this is basically going to be equivalent to 2 delta energy, which is around ef. Okay, so basically that is what I am writing, and I would like to estimate how much is this this delta k gap, this delta k in the momentum space, how much is this delta k. So you can easily open out this bracket, and m star is equal to twice of m because of Cooper pairs. So h cross square by 2m star, if I open this out, this is equal to 4 times kf delta k is equal to 2 delta. Okay, and if I put m star is equal to, if I put this here and if I simplify, then I will get h cross square kf by 2m delta k is equal to delta. Okay, now this is, of course, this delta and these delta are not the same. This is just the difference delta. This represents the difference delta. Okay, please note, so what I can do is, instead of writing capital delta, let me change this to small delta. Small delta, otherwise you will confuse it with the Cooper pair gap. So this is small delta, small delta. Okay, so this is small delta and this is small delta. Okay, so this is basically equivalent to saying that h cross square kf square by 2m delta k by kf is equal to capital delta, or 2 delta k. Okay, the width of this region is 2 delta k. This width in momentum space is, of course, 2 delta k. Okay, 2 delta k is equal to 2 delta, the gap, kf divided by ef, because this is nothing else but the Fermi energy, ef. Now the argument is as follows: the change in momentum of 2 delta k corresponds to a real space variation of the Cooper pair wave function by, let's say, delta x. This is just from the uncertainty principle. This is your uncertainty. This is your uncertainty relation. That the change in momentum over 2 delta k corresponds to a real space variation of the Cooper pair, a wave function psi BCS by delta x, which is basically the size of the Cooper pair, which is approximately the distance over which the psi BCS varies slightly. Okay, so the delta x into 2 delta k is the one, okay, uncertainty relation. And this is your coherence length. Therefore, xi naught is 1 by 2 delta k, which is equal to xi naught is equal to EF by 2 delta into KF, which is equal to h cross square kf by 2 delta, okay, into 2m, which is h cross square kf by 4m into delta. The Fermi velocity is h cross kf by m for an electron. So xi naught is h cross vf by 4 delta. Okay, if you put it in that expression, this will give your coherence length, which is the typical size of a Cooper pair, okay, which is the distance over which your wave function is going to vary. It is the distance over which the wave function is going to vary, and that is going to be the size of a Cooper pair. So for a size of a Cooper pair, the distance over which the wave function is typically going to vary is going to give you your Cooper pair. And if you recall that in our very qualitative discussion of BCS theory, we had said that the incoming electron causes a charge fluctuation, and the incoming electron causes a charge fluctuation, and the second incoming electron, so once an incoming electron causes a positive charge fluctuation, this electron causes a positive charge fluctuation, and the second electron which is approaching has to approach before this relaxes back, before this positive charge fluctuation relaxes back to the neutral location. The second incoming electron has to approach it, and then that gives the distance which is the coherence length. Okay, so they have to be within the distance of coherence length. Okay, the VF, the electrons are moving. So how much is this distance? The distance between two electrons, this distance is Vf into T, which is equal to D, because the electrons are moving with a velocity Vf. Okay, and T is going to be given by the Debye frequency. So this is going to be 2 pi by omega d, okay, because omega d is equal to 2 pi by t. So this is of course your xi naught, okay. So if these two electrons have a spacing of the order of d between them, okay, then this d is of the order of vf into t. So they have to cover this distance d in this time interval t, which is given by the Debye frequency. So xi naught is basically going to be given by xi naught is approximately Vf into 2 pi by omega d, okay. So this is going to be roughly h cross Vf divided by h cross omega d, and to a leading order, delta is of the order of this is of course 2 pi out here. You have these factors 2 pi which we are not going to really consider. So this delta is of the order of h cross omega d, okay. Delta is of the order of, actually it is 2 h cross omega d. So you can actually consider this as if I do it 2 out here, I will put 2 out here. So xi is roughly here, of course you are off by a factor of 4 pi h cross Vf, okay, h cross Vf by delta, okay. Of course this is a very crude approximation, but this gives you somewhat of an approximate estimate of your coherence length, which what you get with exact with your Cooper pair formalism is, this is though your earlier estimate was an overestimate, but you get a reasonable, at least the factors of h cross Vf by delta turn out to be roughly correct in this way of doing things, okay. So this is your coherence length that you can get for the Cooper pair, okay.